So welcome all. Today we are going to see something about concurrency control in distributed system. So in distributed system we are actually going through distributed transactions, and in the previous videos we have seen how transactions can be distributed flat or nested, and how atomic commit is used to commit the transactions. Okay, so now we are understanding that several transactions can be running concurrently in our distributed system, and these systems, as they are multiple servers, so they may be executing these transactions which are involving multiple servers, and on each server different transactions may be executing or using the data objects. Now the thing is, we have to maintain concurrency. I should say we have to control the concurrency, right? So each server manages a set of objects and is responsible for ensuring that they remain consistent when accessed by concurrent transactions. So each server is responsible for applying concurrency control to its own objects. So here we will see something about locking and time stamping, which will enable these transactions, I should say enable these servers to maintain the control the concurrency. So let us say locking. You already know how this locking works. The thing is, transactions are going on, they are accessing data objects, and as the data objects are needed, they are saying that take lock, get a lock of that particular object and then perform your operation. Okay, so this is in distributed transaction also. Multiple servers are there. Each server will have its own lock manager. You will call it a local lock manager. They will decide whether you have to grant the lock or make the requesting transaction wait. So this is a simple example. You will say this is a transaction T and you could say. So here it is taking a lock on data object A at X, and as the time passes, the transaction U, it is taking a lock on B. Okay, and after that this transaction T needs a lock at B, wants to read this B, but B is not available, so it is waiting for U. Okay, at Y, and here U then tries to read A, and it is waiting for T, so that T releases A, then we can use it. So these kind of things may happen when we are using locking, and because of this transaction may enter into deadlock situations. So whenever a deadlock is detected, a transaction is aborted to resolve the deadlock. So in that case the coordinator will involve and will abort the transaction, whichever transaction it finds suitable for aborting. So this happens in locking, right? Now the other thing is time stamping. What happens in time stamping? That in a single server transaction, what happened? The coordinator issues a unique timestamp to each transaction when it starts. So for each transaction you have a unique timestamp, and this timestamp will be used to set as a priority for the transactions, like whose timestamp is more, right? So we require that each coordinator issues a globally unique timestamp. Okay. Other thing is if we have other I should say transactions, I should say servers. Okay, if we have other servers, then also we will need them to roughly synchronize with each other, so that they could issue the same timestamp. Basically, in timestamp, what will happen? You will have a timestamp and timestamp, okay, as well as you will have the server ID. So when you will have this information, this will be actually your timestamp. Now you will use a rule. What is the rule for ordering these things? A transaction requests, right? A transaction's request to write an object is valid only if that object was last read and written by earlier transactions. Okay, and the transaction's request to read an object is valid only if that object was last written by an earlier transaction. Okay, so with this timestamp we will try to find which transaction was earlier and which transaction was later. So this T2 cannot write on a data object which has been written by T3. Okay, and we will also use this timestamping for committing. This will help us in maintaining a discipline that the transaction which came earlier will commit first. Okay, so this is how this timestamp ordering will work. Now you will see something about optimistic concurrency control. So actually what we are saying that we have now timestamps, right? So we can order them. Each transaction is validated before it is allowed to commit. So basically what happens in optimistic concurrency control, actually you will have three phases. First phase, suppose this is the lifetime of transaction. So first phase will be working phase. Then you will have I should say validation phase, and then you will have update. Okay, update phase. So what happens in working phase? It will keep on working. During working phase, each transactions have a tentative version of its operations and the objects that they are working on. Then this tentative version actually is a copy of the most recently committed version of the object. So it then performs a read operation, write operation, whatever it does. However, they will try to avoid the dirty read kind of thing, but still they will work on it, on the data. Then there comes validation phase. In this phase will be executed when client will issue closed transaction request. So when the closed transaction request will come, then it will start validating. It will validate and then it will allow to commit, right? So in this validation, it will check whether its operation on the objects conflict with other operations. So if it does not, then it will allow to update. And then what it will do in update phase, it will update whatever the operations have been done in a permanent storage, and then it will say that it is ready to commit. So with update operation, it will not commit. It is just it will save in a permanent storage, and it will say that it is ready to commit. So such thing may happen. And here in this example, you can see if at all we have this transaction T and U, and they are having read write operations in this way. So what will happen? At X you are having read operation of A, then you can write also. At the same time U was executing and it has accessed B at Y. Now read B, it wants to read the B and it wants to read the A, and this is the sequence. So since this has been completed, B's work has been completed, let us assume if at all B is released, this can be used by this T, so now it will see whether it is possible or not, because the timestamp of this and timestamp of this will be matched. If at all it agrees to do that, we will see. Otherwise, if it is something like this, it is also reading A, which has been read by T. It is reading B, which has been read by written by this U. In that case, there can be, although they all have done this thing in optimistic control, what happens? They all will start working. We will assume that this conflict occurs rarely, so they all will start working, and after they have worked on their local data, then we start validation, and in validation phase we will see whether conflict is there or not. So if here, as we can see, there is a conflict, right? So in such case, what will happen? We will have to abort one of the transaction. So what happens basically in this case? In case of while validation, we detected there is a conflict. So such things can appear, and such deadlock we can call as commitment deadlock. That they were able to do these things, but they were not able to commit, right? So this commitment deadlock is possible in this case of optimistic concurrency control. So these are few things about optimistic concurrency control. Now we are ready to see distributed deadlocks. Let us start this distributed deadlock in our next video. We will try to see what is distributed deadlock, how it occurs, and how it can be represented, what wait for graphs can be drawn, and after that we will see how it can be resolved. The resolving is very simple, that whenever deadlock occurs, we will have to abort one transaction. This is what we have been doing till date. Okay. However, later on, after this thing deadlock detection, we will try to see transaction recovery. What happens if it fails, and can we use something that happened earlier, right? So let us see in the next video. Thank you.